Good evening and welcome to this lecture from the Royal Philosophical Society of Glasgow. First of all, can I ask whether you can hear me at the back? Lots of hands, okay. Somehow stand up and shout if it changes, but that's great. Now I know you're hearing me, I should tell you that if you hear a fire alarm, it's not a practice, so you should leave through either of these doors out through the door you came in, or if you go up, you can go down the stairs and come out at the door you came in, and the muster station is the other side of the road outside the men's union. And could I please remind you to switch off or mute your mobile phones, because phones ringing during lectures is horrible. And then for people who perhaps haven't been to one of these lectures before, generally the lectures last about an hour, give or take. We then take a very few minutes for people who have to leave to catch buses and so on to go. And then we start questions from the floor, and there are roving microphones, which I'll tell you about nearer the time. And people who are listening on Zoom can, as normal, post up their questions, and Pat will forward them to the speaker on your behalf. We finish about 9, and then there are refreshments in the foyer, which you're all welcome to partake of. So that's the housekeeping. It's a very great pleasure to introduce tonight's speaker to you, Professor Sarah Hart. She's a very distinguished mathematician. She took her first degree at Oxford, PhD in Manchester, a number of prestigious postdoctoral fellowships, and then in 2004 took up a lectureship at Birkbeck College in London, where she still is as a professor, now an emeritus professor. And in between 2020 and 2024, Sarah was the Gresham Professor of Geometry. That's at Gresham College, which is a remarkable institution founded in 1597 by Sir Thomas Gresham to provide educational lectures to the public. So we think we've done a lot of lectures, but I think they've probably got us knocked into whatever it is you get knocked into. She was the first woman to receive this honor, so it's great that she's here to speak to us. A special strand in her very distinguished mathematical research is her interest in the links between maths and culture, and particularly maths and literature. And I was doing a bit of homework, and I read an interview, a sort of biographical interview that Sarah gave with a journalist, and the title of the article is "The Mathematician Who Finds Poetry in Maths and Maths in Poetry." And I think that perfectly introduces today's speaker, and it's a privilege to ask Sarah to talk to you about a mathematical journey through literature. Thank you.
Thank you. So it's an honor and a privilege to be here, and I'm very grateful to be invited and to speak to you this evening. I want to begin, though, by saying, we don't often see the words mathematics and literature together. For me, this is a real shame, because, as I hope I will show you, they really are closer than we might think. We think of mathematics often as being solely almost a useful, quote, subject, one that's a part of the sciences. It's used for technical things, and it's put into this box. I don't like putting things in boxes, right? I think this doesn't help any discipline or any subject. Mathematics is often said to be the language of the universe, right? That's why it's so useful for science. Now, that's absolutely true. Mathematics is incredibly useful for science, and it is the language of the universe. Why is it that? Because the universe is full of structure and pattern and symmetry. And mathematics is the best language we know for describing and exploring and understanding those things. So absolutely, it's the language of the universe. But, you know, we are human beings, we are part of the universe. Our brains delight in pattern and structure. We love symmetry, we love symmetrical tiling patterns, we love the rhythms and patterns of music, and we love patterns wherever we see them, and that means it's really natural that patterns and structures would come out in our forms of creative expression. So for me, there's no mystery at all that we might connect mathematics and literature or music or art. And I want to show you just some of those connections this evening. And if we're thinking about structure in literature, if we had to sort of think, where might we find structure and pattern? The place where it's perhaps closest to the surface is in poetry. So let's try and make the slide advance. The slide is not advancing. They'll do it now. Let's see if that will happen. Nope. Nope. And while I'm being helped by my beautiful assistant, I will continue talking. So, poetry has a lot of structure to it. Huzzah! Let's think about the simplest way in which we might see something mathematical, right? Numbers. Any form of poetry will have some sort of constraint or rule. Thank you very much. Here is one. This is the haiku form, right? Now that has a precise numerical constraint. 17 sounds or syllables make up the haiku. So it's quite a strong constraint. You know, you've got to get from setup to payoff in just 3 lines, 5 syllables, then 7, then 5, making up 17 in total. Now this restriction does not stop you being creative. This is something else in common with mathematics. Actually, having some ground rules encourages you to work within that setup, and you have to then be extra creative in order to get your message across. So a constraint doesn't stop you doing that, and being inventive and making beautiful art. It can actually be a spur to creativity. So this is just one example of a kind of poetic form which has a numerical constraint or rule, but actually any form of poetry, if it's not prose, then what makes something poetry? It's some kind of constraint. So it might be something like the rhythm, the meter of the poetry, all those iambic pentameters that we see in Shakespeare, or these numerical constraints, or maybe even something as simple as line breaks. There are lots of possibilities, and poets work within these to make beautiful literature. Now, one example of a kind of constraint we're going to talk about is the rhyme scheme. So this is where you specify which lines are going to rhyme with each other. So an example here of a sonnet we all know, and sonnets have 14 lines, and usually in the English language, they use the rhyme scheme that I'm indicating here with letters. So if you haven't seen one of these before, the A, B, A, B, well, that means the A lines rhyme with each other, the B lines rhyme with each other. So in Shakespeare's sonnet there, shall I compare thee to a summer's day? Day rhymes with the end of the third line, rough winds do shake the darling buds of May. So day and May rhyme, and then all the other lines appropriately following this rhyme scheme. And Shakespeare then, within the rules of the sonnet, can create this beautiful poem that we all love. He's not prevented from making something beautiful by the rules. And just as there are good sonnets and bad sonnets within that collection of rules, and it's up to the artist to create something beautiful within that, in mathematics we have ground rules, we have constraints. We might talk about those as axioms. So if you're doing geometry, you start off with the basic rules. And if you draw 2 points, you could join them with a line, for example. That's a ground rule, an axiom of geometry. And within the rules of geometry, we can do lovely things like prove Pythagoras' theorem. Or maybe there are boring theorems. I have yet to encounter one. But we can do these things within those restrictions. So this is one example of a constraint in poetry. It's a pattern of words. If we understand those structures and those patterns, we can then do interesting things with them. So, little quiz question. Which poet has written the most sonnets? So any Shakespeare experts will know he wrote over 150. I think it's 154 in the first folio, so maybe some more out there. So that's a lot, I think we'd all agree, but that's nothing compared to Monsieur Raymond Queneau, who produced a little book in 1961, whose title, 100 000 milliards de poèmes, translates as 100 trillion poems. And the poems are sonnets. So this is quite a lot. How is this possible? How could you possibly produce a book with 100 trillion of anything in it? It seems impossible. What he did was to understand and use that structure, the structure of a sonnet. So if you get this book, it's a little book, on 10 consecutive pages there are 10 sonnets, one on each page. So it looks like there's just 10 of them. Each of them respect the rhyme scheme of a sonnet, which actually in French it's slightly different than in English, but that isn't particularly important. As long as they're all consistent with each other, they all respect the same sonnet rhyme scheme. But then something else happens. So what Raymond Queneau did was he in effect created a three-dimensional rhyme scheme, because all of the first lines of these sonnets rhyme with each other. All of the second lines rhyme with each other, and so on. So now we've got these 10 sonnets. What you can do is you can make new sonnets by taking any one of the first lines and following it with any one of the second lines, any one of the third lines, and so on. And some editions of the book actually help you to do this physically. So we've got these 10 sonnets over 10 pages. Some editions of the book actually cut the pages into strips. It's like a grown-up version of a child's flip book, right? So you could actually physically assemble the sonnet of your choice. So you can say, I'll have line 1 from poem 3, then line 2 from poem 7, and so on. So then the question is, how many potential poems have we got? And we can work this out with a bit of mathematics. So there's 10 options for line 1, times 10 for line 2. So that's already 100 possibilities for the first 2 lines, right? Because any one of the 10 can be followed by any one of the 10. Okay, so 10 for line 1 times 10 for line 2 times 10 times 10 times 10 times 10. It's 10 to the power 14. That's how many sonnets there are in this book. If you count up all those zeros and work it out, that's 100 trillion. So, brilliant. Now, I love this. I think it's very clever and interesting, and he's used this sort of amazing idea of a three-dimensional rhyme scheme to produce this book of poems. But I think it's a natural question and a completely fair question to say, is this art, right? Is it art or is it just artifice? Is it clever or is it clever, right? We want our art to do something more than be clever. For me, this little book crosses that threshold. I think it is an interesting piece of literature, worthwhile piece of literature, because it raises fascinating questions about, okay, do these poems really exist? That's the first thing. And then who wrote them? So when I say, do they exist? And who wrote them? Well, we can make all of these poems, but Raymond Queneau has written these poems, okay, but can he really be said to have written a poem that you've never read? And I know he has not read all of these poems. How do I know? Well, because if we were to start now, we're not going to, if we were to start now and work through all of these poems, and let's read them fairly, rapidly, let's read one sonnet every minute until we're done. So we're going to be in this room a while. And you think, like, how long are we going to be in this room? Well, if you work it out, which I did, we're going to be late for dinner. 190 million years late for dinner. So we're not going to do that. No one could do that. So Raymond Queneau has not even read, could never read all of these poems. So how can you say he's written a poem that he hasn't read? And also, if we are choosing the lines and making a poem, we've had some input into that process. So have we written that poem? Well, that doesn't seem right, because Raymond Queneau has written every single word of every single line. So how can we be said to have written? And this becomes really relevant now that ChatGPT and other large language models are making text by looking at all of the internet and putting together in different ways, right? That's basically what they do. Well then, if ChatGPT picks the lines, has it got any credit here? Does it get any intellectual copyright? So these are questions we're grappling with right now about when, AI creates something, is it creating it, or is it just jumbling up things that already exist, and how do we apportion these kinds of intellectual copyright? So for me, this is a great way to think about those kinds of questions. So this wonderful book of 100 trillion sonnets is just one instance of where we can understand or exploit the structure and pattern that we see in poetry. I want to talk, though, now about something broader than poetry in terms of structure, because it's not just in poetry that we see patterns. In fact, any form of writing involves choices by the author that give that form of writing some sort of structure. And you can do this at every level. So I like to think of writing as kind of like geometry, because there's the same sort of hierarchy happening. In geometry, we have points, and they make up lines, and they make up planes, and so on. You can go up in the dimensions. Well, any piece of writing, letters make up words, words make up sentences, sentences make up paragraphs, paragraphs make up chapters, chapters make up volumes. So you've got all these layers of structure, and at any point in any one of those, the author can decide to do something interesting, to add in something. So there are instances, for example, of books. There's a very famous one called La Disparition by Georges Perec, which does not contain the letter E anywhere in it. So that's kind of it. It's interesting. And for me, again, you might think, well, that's just a game. It's not going to add anything to the book. But what he does in this book, the book itself is about a disappearance, about something that's missing, and everyone knows it doesn't feel quite right. There's something isn't there in the world, and you get all these clues like there's an encyclopedia with the 5th volume not there, or there's a hospital ward where there's nobody in bed number 5. So you get all these sort of hints in the text that is itself describing what's happening in the story. So yeah, it's a very interesting book. So that's a constraint, a restriction at the level of a letter. And actually you can use maths to work out how hard it is to write a book like that. It's pretty hard to not use any of the letter E in a whole book. I want to give you an example of a constraint kind of at the other extreme of this hierarchy, and that is in Eleanor Catton's book, The Luminaries. So this won the Booker Prize in 2013. She was 28 years old when, so yeah, it makes us all feel perhaps quite old. Certainly I feel old thinking that someone won the Booker Prize age 28. Anyway, it's a brilliant book, wonderful book by Eleanor Catton, her first novel. It's got everything you could want from a plot, this book, The Luminaries. So it's got love, it's got betrayal, it's got stolen gold, it's got murder, it's got intrigue, it's got opium, it's got anything you could want from a plot, it's got it. Brilliant. But one of the themes of the book is about the interplay between chance and fate and how much we're in control of our destiny versus things outside of what we can influence coming in and kind of battering us around and forcing our fate. So to align with that kind of idea of this tension, Eleanor Catton has a sort of running undercurrent of astrological ideas. Now that's not the maths bit, there is a maths bit coming. So for instance, in this book there are 12 key characters, and each of them is loosely associated with one of the signs of the zodiac. And various things about the way they act are kind of related to where the stars were in the night sky at the moments when the action is set. The luminaries of the title, that's the sun and the moon, they are the lovers. And their planetary bodies are moving around as well in amongst all of these constellations. So this is kind of a metaphor for the uncertainty around chance and fate and free will and all of these things. Now, mathematically, the cool thing about this book is that to tie in with the 12 that's going on with the zodiac signs, the book is divided into 12 chapters or sections, and each chapter is half the length of the one before. So that's kind of gets quite interesting. So this halving, it mirrors the waning of the moon. So again, it ties in with the themes. It's not just done randomly, but it has a very strong effect on your experience of reading the book, even if you don't spot exactly what's happening. You know, this halving and halving, the chapter's getting shorter and shorter. And I'm going to show you visually what this does for the reading experience. So here's chapter 1, right? That's first chapter. Chapter 2 is half that length. There it goes. Chapter 3, half again. Chapter 4, half again. Then we're going to fit in that little gap, chapters 5, 6, 7, and 8. And then chapters 9, 10, 11, and 12. So what you are seeing here being produced is this beautiful spiraling effect where the pace is gradually quickening, kind of the gear wheels are tightening, and you're coming to sort of the crunch point by that very shortest final 12th chapter, which is just a single conversation between the two lovers. It's set chronologically somewhere in the middle of the action. So what we know as readers, what we can sense as readers, is that what they don't know, that actually their fate is already sealed. They're trapped within this spiral of fate. And so, you know, it's a really brilliant structure to choose for this book, and it works wonderfully. Now, I've shown you this picture that illustrates the chapter lengths. You could already see from this that the first chapter is more than half the length of the book. So it's one of the, you're reading it for, 400 pages, and then it says, like, 2. You go, oh, I thought it was one of those books that didn't have chapters. You've forgotten that 400 pages earlier it said 1. Anyway, you do then realize, and it quickens up. I want to show you just in slightly more detail the length, how we can work out the length of this book, just by knowing this kind of mathematical fact about it. And hopefully you'll see why soon. So we can think about how long this book is, just in terms of that very shortest final chapter, which will have some length. Let's call it S, some number of words or pages, whatever it is. We don't need to specify. Some length. Now, the one before that is twice as long. And then we double again and double and double and double and double. Kind of 11 doublings earlier, that's chapter 1. So we can find the length of that very first chapter by just doubling 11 times. In other words, we want to multiply by 2, 11 consecutive times. That's 2 to the power 11. And of course, we all know what 2 to the power 11 is, I'm sure. Just quickly work it out in your head. It's 2048. So what this means is that first chapter is more than 2,000 times as long as the final 12th chapter. Every word that Eleanor Catton writes in the final chapter compels her to write 2,048 words in the first chapter. So she's got to keep a pretty tight eye on this. And if we want, if we can work out the lengths of all the individual chapters, we can then add them all up and find the total length of the book. Now, there's a really lovely fact about powers of 2. It's very nice. If you add up the first few powers of 2, like 1 plus 2 plus 4, right, that's 7. That's 1 less than 8, the next power of 2. 1 plus 2 plus 4 plus 8, that's 15, 1 less than 16, the next power of 2. So it's this really nice fact that if you add up the first few powers of 2, the answer is the next one, take away 1. So we don't have to, luckily, because of this cute little thing, we don't need to sit here manually adding it all up. I already know that if I add up all the chapter lengths, that's the first, 1 plus 2 plus all the way up to 2048, the answer will be the next power of 2, 2 to the power 12, take away 1. Now you might think, why is she telling me this? Because another thing that sometimes people might think when we're talking about the mathematics in literature, it's possible that someone might say, well, look, Sarah, you love maths, and that's great, bully for you, but you're finding the maths because you see maths everywhere, which I do. Ask my children, they get very cross with me. I go look at a bus number and go, oh, 257, my goodness, you can make that with a ruler and compass construction because of mathematics devised by Galois in the 1830s. And they say, okay, but can we just get on the bus now, Mum? Teenagers are brilliantly excellent to embarrass. It's a great hobby. Anywho, they might say, Sarah's seeing the maths. You're seeing the maths because you love the maths. But maybe the authors aren't really thinking about it. Is this just something you're seeing because you like it? And so here is my riposte to this. I am absolutely certain that Eleanor Catton knows that 2 to the power 12 is absolutely fundamental to the structure of her book. And here's how I know it. Remember I said that this book, which has lots of wonderful things in its plot, one of the things is a mystery around some stolen gold. Now, there is a court case in the book around this gold, and its precise monetary value is stated. And that number is 4,096. That is 2 to the power 12. So when I read the book, this was like my way into this. That cannot be a coincidence. I'm sitting here reading this book. No one just says 4,096 for no reason. You know, why is that number important? So I think it's a nice little treat for, if you happen to know your powers of 2, it's lovely to see that there. But she's, I think, saying, yeah, I know this, and it's part of what I'm doing here. You know, that missing gold is sewn into the very fabric of the book. So I think that's, Willie says, at least Eleanor Catton, I think authors who use mathematical ideas, you know, they do know that. They are doing it consciously in many cases. Okay, so we've talked about then how we might find structure and pattern in literature, in poetry, but also in novels and all forms of literature. That's kind of the first way that we see mathematical ideas. So, structure. There's another way that mathematics can appear and can have a conversation with literature, and that is symbolism, mathematical ideas, metaphors, and imagery. And even the most fundamental, basic kinds of story use mathematical symbolism. And I'm going to show you. Fairy tales. That's what I mean, like even little children's stories that we all heard when we were young. They are full of numbers. And it's often the same numbers we see over and over again in fairy tales. I'm just sort of illustrating with a few random selections here. So Goldilocks meets 3 bears. Snow White meets 7 dwarfs. Those young ladies walking through the forest, they are the 12 dancing princesses. These numbers, 3, 7, 12, sometimes other numbers like 40, appear over and over and over again in fairy tales. It is not random. I mean, if you kind of think about, let's say the number 3, because I think that's the most commonly occurring. Think about the stories you know, or even like turns of phrase. 3 just seems to be permeating our language and our culture. So even in fairy tales, okay, we've got Goldilocks and the 3 bears, and we've got the 3 little pigs, and we've got the 3 billy goats gruff, and the good fairy always gives you 3 wishes, or so does the genie. And in language, you know, lots of phrases involve 3s. When we run a race, there are 3 medals for the first 3 people. We start the race by saying ready, steady, go, a 3-word phrase, and we have gold, silver, and bronze at the end of it. We learn our ABCs, we don't learn our ABCDs. When we're waiting at the traffic lights, there are 3 different colours of lights. It's just sort of everywhere. It's everywhere. And of course, the 3-word slogan is a very common thing in politics, and sometimes, unfortunately, can be quite persuasive when we wish it weren't. So, you know, the 3 is just everywhere, and actually in so many forms of disciplines, you get 3s, and people often come up to me and say, oh, I'm a whatever, there's a rule of 3 in flower arranging, architecture, comedy, whatever it is, that there are 3 seems to be very powerful. And I think that there's a mathematical reason for that. So I'm going to illustrate it by telling you a kind of trope of a story, right? There's a typical kind of fairy tale that is something like 3 brothers go on a mission, okay? So you can probably, this won't be a surprising story because we've all heard a story like this. So with 3 brothers, and you've got, you know, the oldest brother, he thinks he's pretty great. He goes off on his quest, and he fails. Right? That's one data point. Got 1 point there. Brother number 1, who thought he was brilliant, has failed. Okay? 1 point, isolated. We don't have anything to really be able to predict. Now, brother number 2, the second oldest brother, goes out on the quest, and he fails. Now I've got 2 points. Right, geometrically, what can we do with 2 points? We can make a line that goes through them. 2 points define a line. And if you've got a line, got a direction of travel, you can then anticipate what's going to happen next. Like, okay, I know this, I know what this pattern is. Fail, fail, then the third brother comes along, the youngest, overlooked brother. Everyone overlooked him, and but really he was the bravest and kindest of them all. Okay, he comes along, and he subverts our expectations. He does something different. Geometrically, 3 is the smallest number of points that can define something that's like a whole higher dimension than a line, a shape. It can make a triangle. So you need 3 points in geometry to do something that's kind of more interesting than a line, and it kind of goes up to the whole next dimension. And what we're doing here in the story, 3 is the smallest number of iterations of an event that allows you first to set up an expectation and then to subvert it. And this is just, I think, why fairy tales, which are the simplest kinds of story that we tell to the youngest children, it's like the bare bones of a structure. This is the minimum amount of things that will allow you to do this and have a surprise. And actually, many jokes are structured in the same way. So there's a joke format that has 3 people, and depending on your choice of cultural prejudice, it'll be 2 sensible people and an idiot. Choose your own biases to insert exactly who those are. And then the 2 sensible people are confronted with a situation and react sensibly. And so you've got an expectation, then the third one comes along and does something silly, and then we laugh. So again, we've subverted the expectation, and this time for the purposes of comedy. So 3s have this power, and it's related to, going from a line up to a triangle. There's another thing about 3, which is around equality, because you can draw 3 points that are all the same distance from each other if you make an equilateral triangle. You can't do that just on a piece of paper. You can't do that with 4 points or higher numbers. So that kind of very strong symmetrical shape, the triangle, is a really powerful kind of object geometrically. And because all the points are the same distance from each other, you get these ideas of equality and fairness. And so we think the 3 musketeers, right? One for all and all for one. So there's this other kind of theme that happens with 3. And this is why I think we get 3 so much in fairy tales, but also in language. It's kind of the completion of that triangle, which is a very powerful motif. Now, we could talk about all sorts of other pieces of mathematical imagery that get much more sophisticated. We could talk about how Tolstoy uses calculus in War and Peace. And maybe we will in the questions afterwards. But I thought I'd give you, because 3 is such a great number, we've had one example, which is numbers in fairy tales. I'm going to give you 3 examples in total of symbolism or imagery that's mathematical in literature. And the next one is really my way in, was my way into writing and thinking on a kind of more academic level about mathematics and how it relates to literature. And it's from Moby-Dick. So Herman Melville's Moby-Dick, this is one of those books that we all ought to have read, I rebelled against that because I'm, contrary. And I didn't read Moby-Dick till I was really quite old, and old enough that I should have done. And one day I thought, okay, I'd better read Moby-Dick. And I wasn't expecting to enjoy it, but I did enjoy it. It's fabulous. And right from the start, I noticed, here is someone, this writer likes mathematics. He likes mathematical ideas because he just sort of throws them in as the story goes along. And no one's got a gun to Herman Melville's head saying, now, make a lovely metaphor about infinite sequences. They are clearly, these things are part of the furniture of his mind. When you're an author, when you're reaching for a bit of imagery or a metaphor or an illusion, you look in your brain and something will come out. So you can tell by reading this book, there's just a lot of mathematical ideas that come out, and he clearly enjoys them. So Ishmael, the narrator of Moby-Dick, he does a lot of daydreaming and thinking, and often his thoughts are mathematical in a very interesting way. So I wrote about this and about Moby-Dick and the mathematics in it, and then I thought, oh, this is kind of fun. Let's do more with literature. And so this is how we've come onto this trajectory. So because of that, on the cover of my book, there's a whale, and that's why it's there. If you were thinking, why would that be there? Let me tell you then about my favourite mathematical illusion in Moby-Dick, because it involves my favourite curve. And it's a curve that I want to go on a sort of publicity campaign for this curve, because we've all heard of parabolas, we've all heard of other things, but the curve I'm going to talk about, the cycloid, actually, if you haven't studied mathematics to a kind of fairly high level, you may well not have heard of it, but it's a lovely, lovely, simple idea. I'm going to show you one being made now. Here it is. So it's really nice. You take a wheel, you roll it along a road, and you look at just one point on the rim of that wheel and just follow where it goes. And what you find is that you produce these sort of arch-like curves, and that arch-like curve is called the cycloid. It's a really natural question, like what shape is this? And people started thinking about this. Galileo said he thought cycloids were brilliant, and he said he'd spent 50 years thinking about them because they were so fascinated. He gave them the name cycloid, and people weren't sure what shape that is. So what is that? Some people said maybe it's like half an ellipse. Could be. It's not quite. It's not an ellipse. It's something new. Galileo was fascinated by these, and he was wondering things like, okay, what's the area underneath that arch? Because when we've got a curve like a circle or something, you know, we all learn what's the circumference, what's the area. These are the two basic facts we often ask about curves. So what's the area under here? Galileo didn't know, and he couldn't kind of mathematically find out what it was. So he even went to the lengths of making a cycloid out of a sheet of metal. They're producing one out of a sheet of metal, and then he weighed it, and from that he got an estimate of the area, and it was a number sort of roughly around 3. So he thought, well, okay, if I've got something I'm making with circles, and I've got a number that's sort of 3, maybe it's pi, right? Maybe it's pi times the area of the circle. It isn't that. It's something even simpler and more beautiful. It turns out the area under that arch is exactly 3 times the area of the circle that makes it. It's a really lovely, lovely property. And actually, loads of mathematicians, showing you a few of them here, loads of mathematicians around that time, for the next couple of centuries, got absolutely fixated on the cycloid. Everyone was studying it, everyone was fascinated by it. So that statue you can see there, that is the statue in the Louvre Gallery of Blaise Pascal, mathematician, theologian, very, very well-known mathematician. And you may not be able to see on the slide, but the thing he's looking at there on that stone tablet, that is essentially the picture I just showed you, the cycloid being made. His one wasn't moving. So he's memorialized forever as studying this curve, the cycloid. He, in fact, gave this curve the credit for amazing medicinal powers, because one night he had a terrible toothache, and to distract himself from the pain of that toothache, he thought about the cycloid. And his pain went away, and it was a miracle. So he went on to study it, and he thought this is kind of a thumbs up from God that it's okay to do mathematics and think about mathematics. So that's good. So many other people have studied this curve. I've written a few of their names there, and it got this nickname, the Helen of geometry. So Helen of Troy, famously very beautiful, lots of people who are kind of very interested in Helen of Troy, and lots of people are very interested in the cycloid. But there's another component to this, because Helen of Troy also, let's say, started a few squabbles, let's put it mildly, and so did the cycloid, because all of these people were arguing over who thought of what thing first. These priority disputes, I proved this, I did this thing about tangents, whatever it is. Descartes and Fermat had a spat. So Fermat said that what Descartes had said about the tangents to the cycloid was ridiculous gibberish. So that's quite a referee's report for you. Anyway, so there's all these squabbles around it and everyone trying to do stuff. Christopher Wren's in there. He was the first person, he dabbled in architecture, but he really is a mathematician. He was the first person to work out the length of this cycloid. And it's another beautiful, beautiful, simple relationship. So the area under the arch is 3 times the area of the circle that makes it, exactly, lovely. The length of the arch is exactly 4 times the diameter of the circle that makes it. So again, really just a really simple expression. Very, very nice. Okay, so what does our friend Ishmael have to say about cycloids? Well, there's a passage in the book, in Moby-Dick, where Ishmael has a horrible, dirty job to do. He's got to clean out these great big cauldron-like vessels called tripods. And it's where they like render down the whale blubber. It's really horrible, they get very messy, and then you have to clean them. So he's standing there in this tripod, and he's just sort of daydreaming away while he's got this soapstone cleaning. And he says this: it's a place for profound mathematical meditation. It was in the left-hand tripod of the Pequod, that's the ship he's on, with the soapstone diligently circling around me, that I was first indirectly struck by the remarkable fact that in geometry, all bodies gliding along the cycloid, my soapstone, for example, will descend from any point in precisely the same time. So what he's talking about there is another amazing property of the cycloid. And it relates to this, it's called the tortichrone problem. And this was something that people were wondering about. They wanted to make better clocks. So when you have a pendulum clocks are pretty good, but, you know, and they're good because they have a constant period of backwards and forwards. It's always in the same time, or at least almost the same time. It's actually, when you do the mathematics behind it, it's almost constant, that backwards and forwards, but it isn't quite constant. You have to make some approximations. So mathematicians were wondering, well, is there a curve which something could move along where no matter how high or low you released it from, it would actually get to the bottom in the same time? And this seems, why on earth would such a curve exist? Seems impossible, right? Because surely if it's higher, it's going to take longer to get to the bottom. It's got further to go. But if it's higher, then it picks up more speed, right? It's going to go faster. And so, because it's got more potential energy. So it's higher up, it goes a bit faster. Is there a curve that makes these things exactly balance out? And the cycloid is that curve. There is exactly one solution to this, and it's the cycloid. And this is one of those times in maths where it's so brilliant because you've got something that you found out about over here, and then it turns up over here in a completely different setting. And every so often that will happen in maths. And then if you sort of think, have humans invented mathematics? And then somehow, you know, you've got pi or something over here, and then it turns up over here in the equation for the bell curve in statistics. You think, I didn't design it like that, right? So this is my argument for mathematics is discovered, because we often find these amazing connections. And this is one of them. So this is this beautiful fact about the cycloid that Herman Melville just drops in, just really great, just drops it in and gives us a lovely thing to think about. So in all Melville's writing, actually, you find these beautiful mathematical ideas and illusions. He was very good at maths at school, by the way. He won a prize for being the top of his class in maths. His prize was a book of poetry, which I think is absolutely spot on. So I want to show you next an example. This is my third example of imagery that's sort of mathematical in nature. And this one actually has a kind of mathematical piece of imagery that runs throughout the length of the book. And when I show you the title of the book, you'll say, oh, well, yes, okay. But there is more to it. There's more to it than we might think. Life of Pi, right? So this is, I'm sure many of us are familiar with this. It's a wonderful book about this boy whose nickname is Pi, Pi Patel, and he gets stranded on a little boat in the middle of the ocean for 227 days with a very large and rather grumpy Bengal tiger named Richard Parker. And so this book, it begins, so Pi is telling us his story, and his name is not Pi, like the number pi, but due to a family friend when he was born, a close family friend of the family was obsessed with swimming and used to constantly talk about the swimming pool in Paris, the Piscine Molitor. So this little baby was named, so the story goes, Piscine Molitor Patel. But when you go to school and your name's Piscine, sometimes people might make jokes because it sounds a bit like maybe a ruder word. So at some point he says, okay, right, my name is Pi, and he goes up to the front of the room, the classroom, and he draws a picture of a circle, marks the diameter, says 3.14, I am Pi now. And he says, I took refuge in this number, in that elusive, irrational number with which scientists try to understand the universe. I found refuge. And so, okay, fine. He found refuge in this number. But all the way through the book, there are these little subtle allusions to things that are actually mathematically properties of the number pi. So the first of these is that he says that pi is an irrational number. So what does that mean? Well, it means, irrational means you can't write it as a ratio, you can't write it as a fraction. So when you try and write it down as a number, you have to do it in a decimal, and it goes on forever and ever and ever. It never comes to an end. So that's what an irrational number is. But all the way through the book, there is this kind of play on words, because Pi is telling us, the boy, telling us this story of being on a boat with a tiger, and then he goes this strange sort of land which is made of plants, and all of his recollections are perhaps sort of surreal, and there's this constant question, is this real, is this not, is it imagined, is Pi rational? Okay, so there's the boy rational, is the number rational, so the number Pi is irrational, is the boy irrational as well? So there's this kind of undercurrent of that. But the other part of this is because the number is irrational, it goes on forever and it never comes to an end. And Pi Patel says he hates bodging and ending. He hates things that don't come to a nice ending. He says, I'm telling you the story of my life, and I want it to be able to have a beginning and an end. And he says, I don't like this number that my name is associated with, because it doesn't have an end. It doesn't have a nice end. I would love to be able to tell my story in exactly 100 chapters, no more, no less. Well, actually, the book does have exactly 100 chapters, so that's quite nice. But there's another little bit of cleverness that Jan Martel uses. And it's to do with this time that they spend at sea, Pi, Patel, and the tiger. It was an interview with Jan Martel where he said something quite surprising. He said that originally the iconic animal that this tiger, it's such a great part of the book, it wasn't going to be a tiger. It was going to be a hippo. I feel like that would be a different book, right? But he said, I realized I couldn't use a hippo because hippos are herbivores and they'd never be able to survive for 227 days at sea. So I had to make it a carnivore, so I made it a tiger. So what that tells us is that the fact of 227 days was more important to this book than the tiger being a tiger, right? So why is that? And I suddenly realized, okay, he's done something here. Pi Patel doesn't like the fact that pi is irrational. It can't be written as a fraction. But there is a fraction that is very, very close to pi. It's a really good approximation to pi. And that fraction is 22 over 7. So I think he's given us, in this 227, he's just given us a nice little kind of bit of sleight of hand that makes pi close to rational. And maybe that's true of the boy as well. So there's lots of these little references in the book throughout to the number pi and its properties, as well as this boy's story, which I think is great. So this has been the second then way, symbolism. We talked about structure. We talked about symbolism. And you'll be pleased to know this lecture has a luminaries-like structure, because every section is half the length of the one before. With our final little section of the lecture, and third section, is that there's one other way that mathematics, well, probably several ways, but one other way I'm going to talk about in which mathematics can emerge into literature, and that's when it's openly part of the story, a mathematical theme, a mathematical character. So I'm going to finish with one example of this, and it's the book Jurassic Park. So, we talked about the great American novel. Let's talk about a not quite as great American novel, but still quite fun, right? So Jurassic Park, I imagine we all know the basic story, even we probably haven't read the book, perhaps we've probably seen the films or at least know what they're about. So just sort of slight recap. In this story, you've got some scientists who find a way to clone dinosaurs, and instead of sensibly opening a research institute, they decide they're going to open a dinosaur theme park with not very good consequences. So one of the ideas in this book is about the mathematics of complex systems, chaos theory. There's a mathematician character in the book called Ian Malcolm, and he says, look, you think you've got a handle on this, you think you are controlling this environment, but it's far too complex for you to really be able to do this, and so, things will go wrong. So in the films, that character, Ian Malcolm, is played by someone with absolutely normal and average levels of charisma for a mathematician. That's Jeff Goldblum. Totally normal, any maths department. So he says, look, chaos theory means things may well go wrong. So what he's talking about there is the idea that if you have a complicated setup, a complicated system with lots of different factors happening, then you might have a mathematical equation or model that you think will be able to predict what's going on. But that model is doomed to fail. It's like predicting the weather. We may be able to predict the weather for a day or two out, maybe 3 or 4 days, but ultimately these systems are so complex that we're not able to predict at long range. And the reason is that those kinds of systems are very susceptible to the initial numbers that we put in, the initial conditions. And it's often described in terms of the so-called butterfly effect, which says, look, a butterfly in the Brazilian rainforest, flapping its wings or not, will create tiny little eddies and air currents, and those sort of cumulatively will have, the effect of them will magnify and magnify, so that, 2 weeks later, you either have blue skies or you have a hurricane. And these kinds of systems that are susceptible to, the model not being able to cope with tiny changes in the initial conditions, this is the kind of thing that is being warned about. And yes, indeed, things do go wrong. To spoil the plots for anyone, but yes, it's not great. So in the book then, and also in the films, you've got this mathematical ideas being discussed. But the book does something extra. It illustrates these kind of ideas with another bit of mathematics that I want to show you. The book is divided into 7 parts. They're called iterations. And at the beginning of each part, you've got this diagram that kind of evolves and grows throughout the story. So I want to show you what this is. It's a really simple idea, really simple, and it's very, very pertinent because we think, you would feel like we would be able to understand this thing, but then it gets quite complicated, just like we might think we could understand and control a theme park. So the idea is this. I'll show you a picture, right? This is the picture. This is not very illustrative, but if you can't see my hands, you get a piece of paper, narrow strip of paper, and then you fold it in half, okay? That's kind of step one. And when you unfold it, you've got a bent piece of paper, right? You've got a kind of L shape here, fine. Okay, that's doing it once. But if you do it twice, so bend it, fold it in half, and then fold it again, make a little fold, and then unfold it, now you've got, so I don't know what that shape is, but it's got a couple of bends in it, and we're sort of seeing that being made. And then maybe you do it again, and at each stage, you get a zigzaggy kind of paper strip, right? But it feels like this can't be too hard to understand. You're just making a few bends in a very organized way. So if we had an afternoon, maybe we could work out the formula for what this thing's going to look like. So after a while, you get your piece of paper, you can't fold it accurately anymore, so we need something better. So you can just get a machine to do this, not physically, but you can replicate this process, because all you're doing really at every step is you're taking any bit that's a straight component and you're just putting a bend in it, alternating left and right bends to mimic the folding of the paper. So you can produce these kind of pictures then, step 1, step 2, step 3, and so on. Now this is what is happening in the book. The first iteration, first chapter, begins with actually that 4th picture. Miss out the first few steps. So this is what the first iteration is. Step 4, then step 5, a curve. Actually, that's called the 2nd iteration. And then we've got the 3rd iteration. So we're going along. At this point, it's like lots of straight lines. You sort of think, well, it's getting a bit complicated, but I could work out what's going on. I'm sure the dinosaurs will be fine, and we're at that level of overconfidence. Right, here are up to the 7th iteration. So 4th iteration, 5th, 6th, 7th, right? At this point, this is starting to show some really amazing, unpredicted kind of effects. And if we were to continue this, to infinity, what we've created here is an example of a curve that's called a fractal. They're produced by iteration, by repeating the same process over and over again. And this instance, it's showing one of the characteristic things of this kind of curve, these fractal curves, which is self-similarity. So you get, within the whole, you've got smaller copies of that diagram, of that curve. So it contains itself within itself infinitely many times. And it's just a fabulously intricate and fascinating structure that just came from folding some paper. And so this is a great example of unexpected complexity coming from something we thought we understood. And so I'm going to finish. I'll leave you with if you want to read more, that's my book. But I will finish with echoing that warning that, as Jurassic Park has taught us, if we don't listen to mathematicians, we will be eaten by Tyrannosaurus rexes. So I'll stop there. Thank you.
Thank you so much. We've got the microphones coming down, or the microphone holders. You're happy to take questions?
Of course, yes.
Sarah's happy to take questions. We'll start with questions from the floor. So if you would like to ask a question, stick your hand up, and there'll be one microphone near the back and one microphone near the front. And if you're asking a question and using the microphone, can you hold it close to your mouth? Because then they'll work beautifully, but if they're too far away, then they won't. So, right. We're open to questions. There's one at the back there. Oh, two at the back there.
Hi there, fantastic lecture. I was wondering...
Hold your...
Oh, sorry. Can you hear me?
That's
right.
fine.
I was wondering, Lewis Carroll's famous book, does that work on a mathematical being system, because he himself was a mathematician? Does that work?
Yeah, so yes, Lewis Carroll was a mathematician. His real name was Charles Dodson, and he was very interested in actually the mathematics of logic, so how we understand the processes of even how we think, right? So we had all these kind of symbolism around logic, and he tried to make it into a mathematically understandable system. So he was very interested in logic, and for me, that is the key mathematical thing that comes out in his writing, because it's all, what he does, it's kind of, Alice in Wonderland, for me, is one long reductio ad absurdum, right? It's, what if this were to happen? What would be the consequences of that? And this is, in fact, a technique we use in mathematics. We say, what if we set things up like this? What can we deduce? What would this universe look like? And what he does in Alice in Wonderland is he says, okay, well, imagine if we could grow and shrink by eating and drinking various things. Well, if that were true, then it would be possible to swim in a lake of your own tears, right? That's just what Alice does at the beginning of Alice in Wonderland. So for me, his writing and also a lot of the other things he did in his life, he's absolutely big fan of word puzzles, of other kinds of puzzles, little conundrums, little kind of hidden acrostics in poetry. He would take an idea and explore it in a kind of mathematical framework. There's lots of these jokes in Alice in Wonderland. It's kind of a mixture of puns, but also mathematical ideas that he explores. So you remember when Alice is talking to the walrus, and they're talking about lessons, right? And so the first day there's 10 hours of lessons, and then it's 9 hours and 8 hours and 7 hours, because they're lessons, so they lesson every day. And then Alice goes, "Oh, so on the 10th day, right, there were no lessons, so was that a holiday?" And he says, "Yes, absolutely." And then she said, "What about on the 11th day?" And he says, "That's enough about lessons." So, she's sort of working through these ideas. So absolutely, Lewis Carroll, he thinks in a mathematical way, and that comes out in his writing. Just the whole way in which his mind works is about logic, however absurd. He follows his own rules, which are absurd, but yeah, it's mathematical for me.
Okay.
Hi there. I just finished reading Ulysses last night after about 2 months, so I've kind of forgotten all the details from my own life now and only have that book in my head. But I wonder if you have any insight into the schema of that book, and also into how knowledge of these kind of these structural forms and processes sort of affects the reading experience, because I found the sections of that book that I was aware of kind of the underlying structure, it was quite different from reading the sections where I didn't know what was going on. I wonder if you have any insight into that.
Yeah, so James Joyce, it's interesting because from the outside, on a surface level, you kind of think of this stream of consciousness thing. You think, well, there can't be any structure, right? This is almost the opposite of structure, but in fact, it's very carefully and closely structured, and Ulysses, is mirroring the Odyssey and in ways that we know about. The 17th chapter of Ulysses is this amazing, he calls it something like a physico, astronomico, chemico, something catechism. And it's structured like a catechism. In other words, questions and answers. And the questions and answers are really mathematical. So it begins with them, the two of them are walking home, and it's like a geometry theorem. Because it's like, well, they walked across the green because the straight line being the shortest distance between any 2 points. And then so they start off parallel, and then at the end of the chapter, after all this kind of fun mathematical in-jokes, they physically stand, kind of representing a mathematical theorem, because one of them is standing in the doorway, and he's making an angle that's like less than 2 straight lines, and then the other one is moving away, and it's kind of like a geometry theorem, but the whole chapter has these absurd mathematical questions in. So there's this section, you'll remember, where they're talking about their relative ages. It's like, well, if he was born in this year, he'd be twice as old as he had been 30 years ago, but then in 40 years, he'd be 800 years older than he would have been if he had been born in this year, and after it's this whole absurd thing. So again, it's playing with the structure of a mathematical question or the structure of a geometrical theorem, playing with it and breaking it and toying with it and making the logic sort of make sense but sort of not, in a way that's absolutely fascinating. But so yeah, Ulysses is full of structure. Finnegan's Wake, the only thing I know about, well, I know something about Finnegan's Wake, and that is in the middle of it, there's a geometrical diagram, which is the proof of the first proposition of Euclid, just sitting there in the middle of Finnegan's Wake. But I think we'd need a true Joyce scholar to tell us what that's doing. Maybe there's one here who could tell us what that's doing here.
Pat, are there any questions from the Zoom? From the Zoom audience? Okay. Okay, Pat, ask a question, and then we've got one down here.
Thank you very much, Sarah. That was great. I wanted to ask you about the sonnets that you mentioned at the very beginning. These random putting together lines that rhyme, okay, there's a pattern in a sonnet, but the pattern is not the sonnet. The sonnet is the message that you get. And these trillions of sonnets, they're not poetry, they're doggerel. And so it made me think about, what is poetry? And it's not only rhyme.
Yes.
Yes. And there's so much more than just the pattern.
Yeah, you're exactly right. And that's why you can have bad sonnets and good sonnets. It's not just, if you make something that rhymes, that is not enough for it to be, I suppose, technically it would be a sonnet, but it's not poetry. So the meaning of the words absolutely matters. And I think this is why, so it's true that actually Queneau did make it so that somehow it, of course we can't test this in all 100 trillion, but the idea was that each poem would make sense. But I agree with you that these poems are not all going to be great poems. So for me, you know, what makes this still an interesting piece of creative art is the fact that, you know, we can then discuss, like, do these things exist and who wrote them and what. So there's a sort of philosophical meaning behind it that rescues it from just being a glorified crossword puzzle, right?
Hello. I was going to ask, when Douglas Adams said that 42 was the answer to the meaning of the life, the universe and everything, is there a subtle hidden meaning to the number 42, or has he chosen a number at random?
I don't believe it's chosen at random, and the reason is because a lot of his early kind of versions of things that would become Hitchhiker's Guide to the Galaxy had Lewis Carroll references in them. And Lewis Carroll loved the number 42. He loved the number 42. And there's loads of references, there's loads of uses of the number 42 in Lewis Carroll's writing. Now, many, many people have speculated, we're just bringing it back again, why did Lewis Carroll like the number 42? And there are lots of theories. I'm not sure I really believe any of them. Some of them talk about, you know, there's 42 regulations of in some religious text. I can't remember the exact details. But I think that's probably where Douglas Adams got it from, and you can see these 42s all over Carroll's writing. So there's in The Hunting of the Snark, there's some 42s, there's some 42s hidden in the Alice books. My favourite one of these is that when Alice is discussing with the Red Queen how old they are, and Alice says, I'm exactly 7 years and 6 months, right? 7 times 6 is 42. That's sort of. But then the Red Queen, I can't remember the exact number, but the Red Queen says she's something like 105 years and 4 months and 3 days. That's not the exact number, but it's some very precise thing. And so Martin Gardner noticed, he's a mathematical writer, recreational mathematician, he noticed that the Red Queen and the White Queen, you know, they come from the same chess set, so they're like the same age. If you take their combined ages, as stated, that precise 105 years, whatever it is, their combined ages come up to some big number of days. That number of days is exactly 42 cubed. It's like, wow. I mean, look, he's not putting that in there. People reading the book aren't going to see that. He's put that in there for his own entertainment. But it's still very, very cool. So yeah, the 42s, I think, have definitely come from Lewis Carroll, but I'm not sure why he loved them so much.
Thank you. Any more questions? There's one here and one there. Okay.
You hinted at scripture there, and I'm not an expert, but it is interesting. In books of the Bible, there's a great play on numbers and chiastic rhymings. In scripture, there's all these books by different authors, and there's quite a bit of numbering comes in, chiastic structures and whatnot. And you mentioned 42. If we take the number 7, which in scripture is meant to be divine, and you half that, that's 3.5, and that's taken to be a low point, a sort of a nadir. And if you then, and 3.5 comes in Revelation, but if you then can say that in 3.5 years, which also comes up, that's 42 months. Whereas 40 is a divine number, but 42 is a pestilence. I'm not trying to convert people, but it is sort of interesting.
Well, yeah.
You haven't worked your way through the Bible, have you?
No. But I mean, there are lots of, there's a lot of things written about numbers in the, I mean, 7 is all over the sevens and 7. You should be forgiven 7 times 7 and 77s and 777. So 7s and 40s very much, and obviously 3, I mean, you know, of course, the Holy Trinity, and that's where you get so many 3s in Dante and other places. So yeah, lots of numbers in the Bible, but I'd have to look into this 3.5. That's quite interesting.
The connections between maths and literature seems to have been about literature written in English. What about Japanese or Russian, or does that apply as well?
Yeah, so they're definitely, I mean, if you think about numbers, for instance, we do get these pattern numbers appearing in different traditions, and sometimes it's affected by the language. So the Chinese have this sort of auspiciousness of the number 8, but that's less for mathematical reasons. That's more because the number 8 sounds like the word for lucky, right? And the number 4 in the Chinese language sounds like the word for death, which I was gleefully told by several people when I went to China many years ago, because my birthday is the 4th day of the 4th month. We're like, oh dear, it's not a good sign. So you definitely get symbolic numbers in all cultures. And they may vary a little bit for kind of local reasons, I guess. The writing, I mean, you certainly get symbolism. So I mentioned Tolstoy. And so he does talk about, I mean, of course, there are lots of ideas in War and Peace, but he does have this metaphor that he uses to talk about kind of human history and its development. And so again, spoiler alert, he's not a huge fan of Napoleon. And so he's kind of against the great man theory of history, where it's like one person is so amazing and everything is because of that one person. So he sort of says, you know, it's not because of Napoleon that this happens, it's because just the general sweep of history meant that these events were somehow inevitable. And so we need to think about history, not in terms of these sort of discrete individuals, but in terms of the kind of the continuum of all of the things that are happening. And he says, in order to understand history, we're going to have a mathematical theory a bit like the calculus. So calculus is the tool that mathematicians use to understand continuous processes, like, you know, moving bodies and accelerations and things like this, that can help resolve stuff like the paradox of Achilles and the tortoise. You can do that with calculus, but if you don't have that technique, you get yourself tied up in paradoxes. So Tolstoy talks about that paradox, and he talks about calculus, and he talks about how actually if we want to understand history, we need to think in terms of the continuum and not in terms of these discrete things. So that's a book in Russian. I mean, so yeah, I have to say, I'm not, you know, I was thinking about the books that I've encountered. So there are some French books, most of it's English language books, but I would love for, you know, this to be a starting point for people to think about, you know, the books that they know and love and see the mathematics in them. And so, yeah, when the book came out in Spain, you know, we had some discussions about the logical paradoxes in Cervantes, in Don Quixote, and yeah, we talk about Italo Calvino, and we talk about, yeah, lots of European authors as well. So yeah, I believe it is a universal thing, in short.
And there's one at this one first and then that one. So this one first and then that one.
You mentioned the number 3 and the links to a triangle. I wondered if you had any thoughts on why the number 7 comes up so often in literature.
Yeah, so I think, I mean, I haven't got an absolutely perfect answer to this, it certainly does, but I believe that these small prime numbers have a certain, I don't know, like they've got solidity to them because you can't break them up into smaller parts. So they have this kind of power of indivisibility. And that means if you're thinking about making, for example, the haiku form, you've got your 17 syllables in total, which is prime, but you split it into a 5 and a 7 and a 5. And because each of those numbers is odd and doesn't have, you can't break it up into smaller pieces, somehow those units feel stronger, that you're not tempted to split the lines elsewhere. There aren't fault lines that are accidental. They're where you mean them to be and they stay there. So I think these small numbers like, well, 3, of course, but I think other reasons for 3 as well, but 5 and 7, I think do get used a lot. I think because they make a unit that doesn't naturally fall in half or split into smaller amounts together. So if you have 7 brothers, you're the 7th son of a 7th son, it doesn't break up in a way that perhaps 8 might do. 8 is 2 4s, and it splits in half and it breaks up. So that's my kind of feeling, but I don't think that's the complete answer, probably, but that's part of the mathematical reason.
A question at the back.
Yes, you point out lots of relationships between mathematics and literature. It struck me that there's obviously similar ones between mathematics and music.
Yeah.
And so obviously other people have looked at that kind of thing, and whether it's the difference between notes like harmonic series, or whether it's the pattern of notes, whether it's we seem to like the idea of there being a fixed number of beats in a bar, a fixed number of bars in a phrase, and so on. Does this just simply mean that humans like order? Are we trying to create things which are order? When we've got order, we're happy.
I mean, I think that's a big part of it. We enjoy patterns. If you think about the rhythms, I mean, in poetry, but also in music, like, what's the first sound we hear? It's the iambic pentameter of our mother's heartbeat. You know, these are consoling things. They are soothing things. Order gives us a kind of calm and solace. And then, of course, if we know the rules, like, we don't have to have absolutely perfect, rigid order all the time. Sometimes you get a little frisson from breaking that symmetry a little bit. So we can choose from having, here's a structure that we like, and then we can play with it. But yeah, I think we do just instinctively enjoy patterns. You know, and little children, they like songs, repetitive songs and rhyming. And as we grow, we want more sophisticated patterns. So yeah, a nursery rhyme is great for a toddler, and then when we get older, maybe we think, okay, actually I'm going to now listen to Bach, which is, you know, order on steroids. So I think that those things, we do enjoy them. And for me, that's because, as I said, you know, right at the beginning, the universe itself has patterns and orders. And so we as successful creatures, you know, the fact that we enjoy those things, I don't think is a coincidence. I think it's because it's how we have successfully managed to understand the world so much. You know, if you can predict when the floods are going to come, if you can predict when the right time is to plant your crops, that's kind of a good thing for a species to be able to do. So it's kind of beneficial to enjoy pattern and order.
There's a question at the back here.
Thank you for a very enjoyable and stimulating lecture. I was thinking of Thomas Pynchon, particularly Gravity's Rainbow and Mason and Dixon, or it might have been Dixon and Mason. I mean, Gravity's Rainbow, the perambula of rockets, was not only a metaphor, but actually a driving point of the whole plot, to the extent he has plots. And Mason and Dixon and the transit of Venus and its importance to the scientific community in the 18th century. And I was just wondering if you had any thoughts on those.
Yeah, so, I mean, yeah, Gravity's Rainbow and Mason Dixon, absolutely stuffed full of mathematical ideas. It's absolutely true. And there are plenty of authors, Neil Stephenson's another one, Cryptonomicon, who, like, openly delight in these mathematical ideas, and they are absolutely at the forefront of, and often very explicit in the plots. I feel like that, so I haven't spent a lot of time talking about those authors, because I feel that actually, if you're reading those books, you probably already like mathematical ideas and are not, you know, you don't need to be convinced that mathematics is interesting and fascinating and wonderful. Whereas what I really want, I want to bring more people into the mathematical fold. And so if I say there's mathematics, you know, even in fairy tales, we have these brilliant mathematical ideas. And that's kind of unexpected and maybe a bit hidden. So I like to talk about those books more, but absolutely, Pynchon is, you know, up there with the most mathematically minded of authors. So yeah, he's great.
Can I ask a question?
You can.
Well, I suppose I'm asking myself. Yes, I can ask a question. I'm chair. It's sort of two questions, really, and the first one, I just wrote it down. Is maths, the language of maths, is that genuinely universal? Or are there cultural variants on it? I wanted to ask that because I found that I'm assuming it is, but maybe it isn't.
So that's a great question, because mathematical truths, let's say, you know, they are true in any language. It doesn't matter. You can't do Japanese mathematics with a German accent, as I read once. You know, mathematics is, if you start from here are the ground rules and you prove a theorem, that is true. Pythagoras' theorem has been known for 2,000 years. It's as true today as it was then. It will always be true. And, you know, kind of unlike perhaps ancient Greek science, which has been modified over the years, we don't any longer think everything is made of 4 elements, but we do still have the geometry that Euclid gave us, and that is that those things have been proven mathematically, and when you've proved something mathematically, it's true. However, I mean, yes, however, those proofs and those arguments, there are some cultural components to this. One is, what do we find interesting and worthy of study? So the Greeks were very interested in doing kind of geometric constructions where you're only allowed compasses and a straight edge. Now doing that and being interested in doing that, there's no mathematical reason why that has to be the thing you're interested in doing. You know, you can find points and you can talk about geometry in a different kind of way. So the things that we choose to study, those definitely are culturally influenced. So it might be that in different situations at different time periods, we have questions that we want to answer, and the mathematics that we develop in order to solve those questions, it will be universally applicable if we've got our proofs right, but different things may develop in different places. So there is a cultural context for mathematics, and that is very important. And that's why, you know, we get different things emerging in different places. It's not that one's better or worse than the other. You know, we have different questions. So that in art, perspective and understanding the mathematics of linear perspective, that was first done in Renaissance Italy. It wasn't done in medieval China. It doesn't mean that in medieval China people weren't as clever as they were in Renaissance Italy. Actually, the art in that region of the world had different questions that needed answers. So you get these great long scrolls that are kind of very long, maybe 10 meters long, representing a story, beautifully artistically drawn. Linear perspective is completely irrelevant to that kind of art because there's no vantage point that works 10 meters long. So the mathematics of perspective that's required for Renaissance art that was being done in Europe in the 15th century gives you linear perspective. In China, you get a completely different kind of perspective that is used. Isometric drawings, essentially. A valid alternative solution that developed there, and over here we had a different one. So both of these are valid things mathematically, but they develop differently for different reasons.
Thank you. We have some questions from the...
There's a question from the online audience. Do you have any thoughts about mathematics in The Simpsons as outlined in Simon Singh's book?
Yes. My main thought is it's a fabulous book that Simon Singh wrote about mathematics in The Simpsons, and I highly recommend it if you enjoy these kind of ideas. So The Simpsons has a lot of people involved with it that have graduate degrees in mathematics. And so it is filled with little mathematical in-jokes. In many of the episodes, you just get these nice little jokes. So one I remember is that, Homer Simpson is always eating donuts, right? And there's this field of mathematics called topology, where you're kind of just interested in not really distances in things, but like, can they be stretched to look like other things? So the topologist, the joke goes, can't tell the difference between a donut and a coffee cup, because an American donut, anyway, has a hole in the middle, and a coffee cup, you could sort of stretch the cup round, it's got that little hole in the handle, so they are both three-dimensional shapes with one hole in them, right? So they're the same if you're a topologist. And so there's this kind of cute little thing in The Simpsons, just that it flashes onto the screen, but Homer manages to like break topology because he's got this donut and then he takes a bite out of it and now it hasn't got a hole anymore, so now it's equivalent, you know, to a sphere. So they just drop that in. They just drop that in, and many dozens of examples that Simon Singh goes through in his book. So it's a very entertaining book, which I recommend.
Thank you. I think that's a good note on which to
Finish-
bring things to finish with donuts and give our speaker a rest. Thank you so much for a wonderful talk. It was brilliant.
Thank you.
Thank you. We haven't quite finished, because it's now my pleasure to give you, in token of our appreciation, Philosophical Society paperweight.
Thank you.
Oh,